Welcome to Similarity in Right Triangles. I'm Mr. Pi, the math guy, and I'm going to be your host today. So let's get this geometry party started. Here we're going to be talking about a theorem, the altitude of a right triangle theorem. I'm not sure if that's an official name or not. After reading the theorem and putting together this presentation, I came up with it myself. The altitude of a right triangle theorem. The altitude to the hypotenuse of a right triangle divides the triangle into two triangles that are similar to the original triangle and to each other. In essence, if you have a right triangle, in this case the original right triangle is triangle A, B, C, and we place its altitude in, it divides it into two smaller triangles that are similar to the original right triangle. So it divides it into two smaller right triangles, and you can see those triangles here, triangle ACD and triangle CBA. And this is the similarity statement. Just the other day in class, before I made this video, we were talking about similarity statements, and a student asked me, Mr. Pi, what's a similarity statement? And I said it's simply like a congruent statement, but stating that two triangles or polygons are similar. In this case, we have an extended similarity statement where we have three triangles being listed as similar to one another. So let's take a look at and actually take a second to see and visualize how these triangles are. And I encourage you, if you're taking notes on this, to copy this diagram down and actually touch the vertices with your fingers. So in this case, we have triangle A, B, C being similar to triangle A, C, D, and it's also similar to triangle C, B, D. And I encourage you to say that to yourself a few times. The triangle A, B, C is similar to triangle A, C, D is similar to triangle C, B, A. Take maybe a minute and do that. Say that to yourself as you touch the vertices 5 to 10 times, and I'm sure you'll have an easier time understanding the corollaries we're going to be talking about. An important concept when studying the similarity of right triangles is the geometric mean, and it's given by the proportion a over x is equal to x over b. In this case, yeah, we do have four variables, but the variable that we're most concerned with is x, because a and b are going to be positive real numbers, and that's a key thing to understand. They're going to be positive. They can't be negative. And we arrive from this proportion down here to this statement as x is equal to the square root of a times b. We get to that place by using the idea of cross products. In this case, we'd have a times b or b times a. We'll write that down as a times b is equal to x times x, which we can write as x squared. Now from there, what we do is we take the square root of each side and we turn that bad boy around, and that's how we end up right here. The square root of x squared gives x, and the square root of ab, for now we just write as that until we know what a and b are, and that's going to be in the next example given to us, and then throughout the rest of this lesson we're going to find numbers for this proportion. But it's important to understand that the geometric mean is the product when these two numbers are going to be the same. In example 1, we're asked to find the geometric mean of the following pairs of numbers. Right answers in simplest radical form. This is a pretty algebraic skill here, just to make sure you understand how to solve something with a geometric mean. And so here we have 3 and 12, and the geometric mean, remember, is a over x is equal to x over b. 3 and 12 will serve as our a and our b, so we substitute in. That gives us 3 over x is equal to x over 12. Then when we solve this, 3 times 12 is 36 on the left for the one cross product, and the other cross product is x squared. We solve this by taking the square root of each side, the square root of 36 and the square root of x squared, And that gives us 6 is equal to x, and I like to turn that answer around, and you usually can without writing the extra step. So in this case, x is equal to 6. In this case, simplest radical form happened to be a whole number. In example B, using the geometric mean proportion, a over x is equal to x over b. We substitute 8 in for a to give us 8 over x. And for b, we substitute in 12, so on the right-hand side, x over 12. When we multiply to get our cross products, 12 times 8, that gives us 96. And on the right-hand side, x times x is x squared. So to solve this again, we're going to take the square root of each side, taking the square root of 96 and the square root of x. Well, the square root of x is x. We need to break 96 down. 96 does have a perfect factor. We can factor 96 into the square root of 16 times the square root of 6. And since we can take the square root of 16 to give us 4, we can write this in simplest radical form as 4 times the square root of 6. So our final answer here is x is equal to 4 square roots of 6. We talk about corollary 1 to the altitude of a right triangle theorem. These are derived from the theorem, so the actual proof lies in the theorem of the altitude of a right triangle theorem. The corollary 1 states the length of an altitude to the hypotenuse of a right triangle is the geometric mean of the lengths of the segments of the hypotenuse. So let's break this down. The length of the altitude of the hypotenuse, that's this length right here. The altitude of the right triangle, WXY, is YZ. This is the altitude, and this is the geometric mean. So what that means is when we set up our proportion, our geometric mean is this number here and this number here. So our geometric mean is going to be the length YZ. So that's the number, or that's the thing that appears twice in our proportion as the geometric mean. And it is the geometric means, and here comes the second part of this, the lengths of the segments of the hypotenuse. So this is the geometric mean of these pieces down here. So that would be the length of WZ and XZ. And this would be the corollary 1 for this diagram. And another way I like to think about it is this. Is that when I put it together, it's this length over this length, and then this length over this length. They all kind of meet down here in the middle. So that's another way to think about it. But this right here, this proportion is the corollary and how the sides are related to these triangles. Corollary to an altitude of a right triangle theorem. The altitude to the hypotenuse of a right triangle separates the hypotenuse so that the length of each leg of the triangle is the geometric mean of the length of the adjacent hypotenuse segment and the length of the hypotenuse. That's a lot of long words, and that means a whole lot. What this breaks down to is that this altitude makes this side the geometric mean, and it will also make this side the geometric mean. It makes two separate proportions here. This altitude makes two separate proportions in which the legs of the big triangle are the geometric mean. So let's take a look at what's happening on the left-hand side. This leg, YW or WY, is going to end up being the geometric mean of our proportion. And our geometric mean, remember, is in the bottom left and the upper right-hand side. So we're going to have WY in the position of our geometric mean. And it's to the length of the adjacent hypotenuse segment, which would be this segment right here, WZ, and the length of the hypotenuse. So the whole length of the hypotenuse. So in this case, that would give us WZ and then WX. So again, like I did in the theorem, when you work this out to start remembering it, this side's the geometric mean, so it's going to be the short segment of the hypotenuse over the leg, and that's going to be equal to the leg over the whole length of the hypotenuse. I like to touch that with my fingers and look at what's going on here. I have WZ over WY, and that is equal to WY over WX, or the part of the hypotenuse over the leg, and that's equal to the leg over the whole hypotenuse. Now we have the same thing happening on the other side here. I'm going to do this in blue, and let me clean this up a little bit. Let me get rid of the red, and I'll put the letters back in. And then on this side, because there's two relationships here, one on the left, one on the right, this side, WX, this leg is the geometric mean, so that goes here, the bottom left-hand side of the proportion, and here in the upper right-hand side of the proportion. And that is the geometric mean to the length of the adjacent hypotenuse piece, which is this here, ZX, and the entire hypotenuse, YX. And I encourage you to go through the process of looking at the proportion and touching and looking at where it's in the angle here. So you have ZX over WX, and that's equal to WX over YX. And again, I encourage you to do that several times so you become familiar with these corollaries. In example 2, we're going to be applying the corollaries to the theorem we're working with in this lesson, and it's the altitude of a right triangle theorem, and we're asked to solve for x and y in this case. We're given a pretty plain diagram, and it's labeled. We have triangle ABC. That's our big right triangle, and we have to figure out the values of x and y. So I typically start with x, so in this case, let's take a look at how we're going to find x. And x is the length of part of the hypotenuse of the big triangle, and we know information about its altitude and the other length here, AD. And there's the first corollary says that this altitude serves as the geometric mean of these two pieces of the hypotenuse. So writing this out using the vertices, we can say that AD over CD is equal to CD over BD. We can substitute the numbers in and solve. So in this case, AD is 6 over CD, which is, AD is 2, not 6. AD is 2. CD is 6. CD is 6 again here. And this is what we're trying to find, the length of BD, which is x. So to solve this, we use cross products. X times 2 is 2x. 6 times 6 is equal to 36. We solve this by dividing each side by 2. And x is equal to 18. So what's actually interesting here is now that we know what x is, it really helps us to figure out what y is. And maybe I'll put right here that this is the work for x. Hopefully you could figure that out down here by that, but if you couldn't, just in case. So here's our work for y. And for y, we're given this information about the leg of the big right triangle, which when you're solving for that or looking for that length or have information about that length, that's related to corollary 2. And so we know that this serves as the geometric mean. So this is the geometric mean, CB, and its geometric mean to this, AB, the entire length, actually we could go DB, the short length, over the entire length of the hypotenuse. And we find that now that we know x, we know the length of AB. So substituting what we know DB is equal to 18. CB is what we're trying to find, y. That's also y here. And then the length AB, which is equal to 2 plus 18, which gives 20. Remember, we have to add these two to get AB. Then we multiply cross products. 20 times 18 is 36. And that'd be 36 with a 0 on it, would be 360. Y times y is y squared. We have to take the square root of each side. The square root of y is y. And the square root of 360, this is a pretty easy one. If you recognize that that can break down into 36, the square root of 36 times the square root of 10. Then running that in a simpler form, that would give us y is equal to 6 square roots of 10. So here we had to use corollary 1. For y, we had to use corollary 2. And here we saw that we needed to find the value of x to find the value of y. Here in example 3, it's kind of a real-world connection if you like to play golf. At a golf course, Maria drove her ball 192 yards straight toward the cup. Her brother Gabriel drove his ball 240 yards, but not toward the cup. The diagram shows the results. Find x and y, which represent their remaining distances from the cup. So here we can see it's broken down as a right triangle. Maria drove her ball off the tee 192 yards straight towards the cup. Her brother Gabriel drove it off to the left a little bit. Maybe he hooked a little bit off the tee. 240 yards. What we have to do is find Maria's distance to the cup and Gabriel's distance to the cup. Even though he drove it much further, he was way off target, so he's going to have a longer target. So let's go ahead and find those values. To find those values, we're going to use those theorems and corollaries we just talked about, mainly the corollaries. And to use these corollaries, we're going to have to find this distance from G to M, that length of that altitude. That's going to be using Pythagorean theorem. We have to find this value right here. That's the first thing we have to do. So to do that, we just take a look at the Pythagorean theorem. A squared plus b squared is equal to c squared. If you're unfamiliar with that, maybe you should try to find a YouTube video to help you out. In this case, the hypotenuse C is 240. B, the one leg, I'm going to make that the leg we know. So that'd be 240 squared. I'm going to make B the leg that we know, 192. And what I'm trying to solve for, that length of GM, is a squared. And let me catch up to speed on what I'm doing. Maybe I didn't make that too clear. The first thing I need to do is find this length G to M. And if we look at this triangle from the T to Gabriel's shot over to Maria's shot, that's a right triangle where this distance from the T to Gabriel's shot represents the hypotenuse. This would be a leg of the right triangle, and this distance from between Maria's and Gabriel's shot would be the other leg. So that's what I'm trying to solve for right now, is that distance right there. So when I square these numbers, I get a squared plus 192 squared, which gives 36,864. 64. And on the other side of the equation, 240 squared gives 57,600. Now here, when I subtract 36,864 from both sides, that gives us a squared is equal to 20,736. When I take the square root of each side, that gives me a is equal to 144. And now that I know this distance right here, it's not a question mark anymore, that distance is 144, I can start to solve for the distances of Maria and Gabriel's shots. Now let me show you what I'm going to do, because even I struggle with this. And what I'm going to do is I'm going to take this diagram, I'm going to turn it around so you can see the right triangle a little bit easier. And this 144 I'm going to put right in there. And Now that we have this together, it's going to be a little more clear on the use of corollary 1 and corollary 2. It's a little easier because the examples we just saw, this is how it was set up. And if you can do so, or if you can't just turn it around, you can make another picture for yourself to help you visualize a little bit easier. So I'm going to start with the distance of x. I naturally start with x. And that distance of x is going to be the relationship from corollary 1 that says the altitude is the geometric mean. So in this case, 144 is going to be our geometric mean. So setting up the proportion, the geometric mean is going to be 144, which means that's the number that appears twice in the proportion. And that relates this length to this length. It breaks the hypotenuse of the big triangle down. So that'd be x over 144 is equal to 144 over 192. Solving this proportion, that gives us 192. X is equal to 20,736. When I divide each side of this by 192, that gives me x is equal to 108. So Maria's distance to the cup is 108 yards. Now we're going to find her brother Gabriel's distance, which is represented by y. In this case, that's the side of the triangle, which means the y in this case is the geometric mean. So when I set up the proportion, I'll do that in red so we can differentiate between the two. The y is going to be the geometric mean, and that gives us a relationship between this piece of the hypotenuse and the whole hypotenuse. So in this case, we solved for x, and that was 108. So that will give us 108 over 300. Now that 300 comes from 192 plus 108. So when we go to solve this proportion, 300 times 108 is 32,400. That would give us y squared. Then we take the square root of each side. In this case, I used a calculator. I didn't try to break this down. I just saw that, punched 32,400 into the calculator, took the square root of it, and it gave 180. So we figure out that Gabriel shot, he remains 180 yards away. So here are our two answers, that Maria is 108 yards away and Gabriel is still 180 yards away. Even though Gabriel smashed the ball off the tee, since he wasn't very accurate, he's very far away from the hole, much further than Maria is, who didn't hit it as far as Gabriel off the tee, but she has a much shorter shot because she was more accurate.